All right, so we are looking at section 6.1, and this is going to kind of be our question for today, but you don't have to write this down, but I want you to think about it, and then when I get back, we're going to talk about it. So I'm going to see your opinions here. So the question is, would you rather have $1,000,000 or be given a penny that will double every day for a month? So that means if I give you a penny on December 1st, then on December 2nd, when you wake up, it'll be 2 pennies. And then when you wake up the next day, it'll be 4 pennies. The day after that, you'll have 8 pennies. So that would go on for a month. So which would you rather have? So I want you to be thinking about this as we go through this lesson here. So you're going to need a few things out. You're going to need your student journal packet. We're going to look at some things in there. You're also going to want a notebook or some graph paper to take notes on. You're going to want a graphing calculator. And then also your textbook. We're going to do a problem out of there. So again, that's notebook, student journal packet, textbook, and calculator. So let's go ahead and go to page 156 in your student journals. That's where we're going to start. Okay, so we are looking at exponential functions here. So that's that first spot. So that's what chapter 6 is all about, is exponential functions. All right, so we're going to define an exponential function as this form. Y equals A times B to the power of X. So notice our variable is in our exponent. So this is very different from like x squared, for example, where our variable was the base. So kind of some of the stipulations here is that a cannot equal 0. So a can be anything but 0, which makes sense because then this whole thing would just be 0. And that our base, b, has to be greater than 1. All right, so then in the core concepts underneath here, looking specifically at exponential growth, this is what these exponential functions are going to look like. So if you think about raising some number to a power, and that power begins to increase, we're going to start to grow faster and faster. So that's exponential growth here. So just a few things we want to highlight here. So the first one is this point, which is your y-intercept. Okay, so this is saying for this function b to the x, my y-intercept happens when x is 0. So this is like b to the 0 power. And we know that anything to the 0 power is 1. So we're always going to have this as our y-intercept because anytime I raise a base to the 0 power, I get 1. Other things I want to think about would be something called an asymptote. So that's what this box is looking at here. They say the x-axis is an asymptote of the graph. An asymptote is a line that the graph approaches more and more closely. And the way we will actually draw in an asymptote on our graphs is with a dashed line. So you want to think about an asymptote as kind of like a boundary. So this, as I move to the left, this function is getting closer and closer to that x-axis, but it's never actually going to touch it or go below it. So it just kind of hovers above it forever. And the reason for that is if I take some base and I raise it to a power, so let's say, for example, 2 to the x, so a very basic exponential function. No matter what I raise 2 to, I'm never ever going to get a negative number, right? So 2 to the first, 2 to the second, 2 to the third, and so on, that starts to grow. But if I go the other way, like 2 to the negative 1 would be 1/2. 2 to the negative 2 would be 1/4. So those numbers do get smaller and smaller, but they never actually get negative, which is why our function gets closer and closer to that x-axis, but never actually touches it. And that's called an asymptote. Okay, so that is for exponential growth then. We'll also look at exponential decay, which is really the exact same idea, except for I'm going down. So decay means I would be going down. So notice I still have this asymptote at the x-axis here, but this time what's different is my b value. So it's all about the base. So when my base is greater than 1 over here, I have exponential growth. When my base is between 0 and 1, I have exponential decay. So this would be like 1/2 to the power of x or something like that. So some number between 0 and 1. Okay, so this is the point where you're going to switch to either your notebooks or some graph paper, and we're just going to do a few examples. So I'm going to give you exponential functions, and we're going to graph them, talk about domain and range and asymptote then. So graph, asymptote, domain, and range. All right, so let's look at our first function here. We're going to do y equals 2 to the power of x. Okay, so we'll get to the point where we start to have some transformations on these functions, but for now they're just very, very basic. So to graph them, we're going to do a little table of values. Okay, and we're going to go from -2 to +2, just to get a good little picture of what this looks like. So 2 to the power of x. That means that these values here are my exponents. So I first want to think about what is 2 to the power of -2. So I know that a negative exponent means I'm going to end up with a fraction, and 2 to the second power is 4, so this must be 1/4. Just like 2 to the first is 1/2. I know anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. So those are some of my basic points here. So let's go ahead and plot those. Okay, so I've got -2 1/4, so really tiny, -1 1/2, 0 1, 1 2, and 2 4. So notice this starts off really slow and then grows much, much faster. So I have these points here. So I also want to make sure I draw in my asymptote. Sometimes I like to use a different color, so just a dashed line to show that my function is approaching the x-axis but never actually touches it. Okay, so when I think about so these things, so we graphed, we want to talk about the asymptote. So the asymptote is a line, so we're going to want an equation. So this is a horizontal line at 0, so that would be in the form y equals 0. So we're going to get to the point where we have asymptotes that go vertical as well, so we want to always make sure we have our x equals or y equals there. Domain then, thinking about x and y, or x values for domain. So this function goes to the left forever, it also goes to the right forever. So my domain would be all real numbers. Another way to think about that is I could substitute in anything for this value of x. It doesn't matter. I can have negative exponents or positive exponents. My range then is going to be affected by that asymptote. So I know this function is going up forever, but I also know that it's never ever going to be negative, or it's never going to go below this line. So whatever your asymptote is, that's going to tell you what your range is. So my y values are always greater than 0. And notice it's not greater than or equal to because I'm never actually going to touch that line. Okay, let's look at another one. Same directions here. So we're going to graph, do the asymptote and domain and range. This time we have y equals 1/3 to the power of x. Okay, so this is one of these situations where my b value is between 0 and 1. So I know I should end up with some decay. So same idea, I want to start with my little xy table, and those x values of -2 to +2 are always going to work. All right, so now 1/3 with a negative exponent is going to flip that. So I'm no longer going to think about 1/3, I'm going to think about that as being 3 over 1 or 3, and 3 to the second power is 9. 1/3 to the -1 power would just flip it, so I would get 3. Anything to the 0 power is 1. Anything to the first power is itself. And 1/3 squared, I have to square the top and the bottom, so 1/9. go ahead and plot those points that we found here. So -2, 1, 2, 3, 4, 5, 6, 7, 8, 9 would be up here. -1, 3. So notice it's going down really, really sharply. And then it kind of starts to taper off some. So 1/3 and 1/9 would be really close to 0. So I have this type of function with decay. So notice I also have an asymptote at 0, so let's draw that in. Okay, and then I want to define those things. So my asymptote is still a horizontal asymptote at 0, so y equals 0. My domain, again, this is going left forever and right forever. So my domain is going to be all real numbers. And since my function is always above the x-axis, my range is going to be y is greater than 0. Y never ever is negative. All right, let's look at one more graphing problem here. So same directions, graph, asymptote, domain, and range. And this time we're going to look at the power of, or 3/2 to the power of x. So you might look at this and say, oh, that's a fraction. It's going to be decay. But this is not a number between 0 and 1. Even though it's a fraction, it's 1.5. So this is still going to be growth because that's bigger than 1. So we're going to start with our table again and look at x values from -2 to +2. So then when I look at this here, so I know a negative exponent is going to flip this. So I'm going to think about 2/3. And when I square each of those, I end up with 4/9. -1 I know is going to flip, so I end up with 2/3. Anything to the 0 power is 1. Anything to the first power is itself. And for squaring, I want to square the top and the bottom. So 9/4. Okay, so then let's go ahead and set up our graph. I'm going to plot the points I have. So this isn't going to be exact, of course, but I know 4/9 is a little less than half. I know 2/3 is a little more than half. So just kind of graphing approximately here. I know that 3/2 is 1.5, and 4/9 is bigger than 2. Then notice this is growing a little bit slower, but still has that exponential growth pattern. The asymptote at 0 because no x value is ever going to make that function negative. So my asymptote is y equals 0. My domain, again, is all real numbers. So that function is going left and right forever. Also, I could substitute anything into this x value here. In my range, this function is getting really, really close to 0, but never ever goes below it or touches it. So y is always greater than 0. Okay. Next here, we're going to look at a problem in your textbook. So this is on page 300. And we're going to look at number 22. So go ahead and get your textbooks out. Pause if you need to. All right, so they say the population P in thousands of Austin, Texas during a recent decade can be approximated by, and they give us a function where T is the number of years since the beginning of the decade. So like T equals 0 would be the very first year in that decade. T equals 1 would be after the first year, and so on. So they want to know, first, is this exponential growth or decay? So for that, I need to look at my base. So this 494.29 is not my base. That does not play into growth or decay. It's only the value that's being raised to the power. So since that base is 1.03, that's bigger than 1, so we would say this is growth. And my reasoning, even though it doesn't ask for it, is B is greater than 1. Okay, they say identify the annual percent increase or decrease in the population. So like if I had 2 to the power of x, so that was our very first graph we did, something was doubling. Okay, so our growth would be like 200% if it's doubling. So they say identify the annual percent increase or decrease. I know it's an increase because it's growing. So what I want to look at is if my base were just 1, that would not be growing at all. It would be staying the same. I want to look at the part that's above 1. So the 0.03, in other words, a 3% increase. So all I'm looking for is what, how far above 1 this is. So 0.03 is 1%. So if it would have been 0.05, my increase would be 5%, and so on. Next thing they say is estimate when the population was about 590,000. So notice they say P is the population in thousands. So what I'm actually looking for is just this part. I want to know when this function is 590. So to do this, now they're just saying to estimate. So what we're going to do is we're going to plug this into our graphing calculators. So I'm going to go to y equals, and I'm going to type that function into y1. So we have 494.29, 1.03 to the power of x. Okay, and then nope, that's it for now. So I'm now going to go to my table. So if you hit second graph, that gives you the table. And what I'm looking for then is when that y value is near that 590 that I was looking for. I don't know why it's not showing up. There it is. So if I look here, I'm looking for where does 590 happen? So there's as close as it gets. So it happens somewhere between years 5 and 6, but really, really close to year 6. So 590 would occur right before that. So we're just looking for where that 590 occurs, and it's between year 5 and 6. So that's all I'm going to say here. So we're just estimating. Okay, last thing we want to do here is talk about compound interest. So this is where money gets involved. So if you've ever had a bank account or a savings account, or maybe your parents have a college fund for you, it uses compound interest. So that means that if I put in $500, the bank pays me interest, and I end up with more than $500 in the end, as long as I don't take any money out. So there are a few things that affect how much money you end up with. So one of those is the principal, and that's how much money you initially put in. So that's called the principal, so that's going to be important to us. What's also important to us is the interest rate. So that's R, expressed as a decimal. So if your interest rate is 5%, we're going to use 0.05. N is also important to us, and that's how many times our interest is compounded per year. So that might mean that my account, they only give me my interest once a year, or maybe they do it twice a year. The most common is monthly, or 12 times a year. And that tells us about A, which is the amount after a certain number of years. So something we might see is I deposit $500. I get 5% interest compounded monthly. How much am I going to end up with after 10 years or something like that? Okay, so I would make sure I circle or highlight this formula. If you're doing notes in your notebook, definitely make sure this is included with what each of these things are. Okay, so we're going to do a few examples that use that formula. So this is on page 158. We're going to do 6 and 7. So they want us to find the given amount. So they say in the account earning compound interest after 5 years when the principal is $12.50, and then they give us specific information for the two different problems. So all I'm doing here is filling in that formula. So I want to find A. So looking back at that formula, A equals P, so 1250 times 1 plus R. So 2.25%. So I have to move that decimal place over 2. So that's going to be 0.0225 divided by N. N is how many times it's compounded per year. So if I say quarterly, quarterly means 4 times per year to the power of T. So I want to know after 5 years, so this is going to be to the 5th power. So go ahead, type this in your calculator just as it is, so parentheses right where they are, and this will work. Okay, so go ahead and pause and do that, and come back and let's see what you get. So I get $1,398, and since this is money, I definitely want 2 decimal places, so in 40 cents. Okay, so if I leave my money in this account for 5 years and don't touch it at all, this is how much money I'll end up with. All right, let's try another one, same idea. So if you're feeling okay about this, this would be a good time to pause. Go ahead and set this one up and try it yourself, and then come back and see how you did. Okay, so what's different this time is the interest rate and how often it's being compounded. So I'm still starting with my 1250, so that's P. So just following the formula here, 1 plus, let's see, 1.25% is a decimal. I would have to move this 2 places to the left. It would be 0.0125 divided by N. So N is how many times it's compounded per year. If something is being compounded daily, there are 365 days in a year. And then this is to the power of NT. So the power of 365 times 5. And I now see that I made a mistake in number 6. I forgot the 4. So NT would be 4 times 5. So if you did that one and it didn't quite come out, that's why we needed a 4 times 5 there. Okay, so here then, let's go ahead and pause and type this into your calculator. So we end up with $1,330.62. So not that different from one to the other. Because this interest rate is a whole % smaller, that's why we end up with about $70 less or so.